Thank you, Diane. Continuing with the theme of the power of the web, there's also the power of technology that's underlying the web. Modern processors, sensors, batteries, and ubiquitous broadband have together helped us advance a long-standing goal of making the web available on any device. Mohammad Reza Haghighat, or Mo, is a senior principal engineer at Intel, focusing on innovation in the web technologies, and he's also leading Intel's HTML5 technical strategy. Mo will tell us more about how access to the full power of hardware will yet again transform our experience of the future web in his talk entitled Bringing the Full Power of Modern Hardware to the Open Web Platform. Mo?
Good afternoon, everybody. I'm Mo. I work for Intel. We like to make things fast. So I'll be talking about bringing the full power of modern hardware to the web platform to be able to make it faster and deliver even more fascinating experiences. JavaScript has become fast, really fast, a couple hundred times faster than a decade ago. And the recent result from the ASM.js project at Mozilla is just amazing. JavaScript performance is approaching that of native. The gap is only about 1.5x. This is amazing. It's JavaScript running with the full speed, almost the speed of native. And using that technology, Mozilla has brought a number of large game engines like Epic, Unreal, 3, 4, Unity to the web platform. Now, this gap, 1.5x, is with respect to sequential scalar code, not the parallel vector code. But modern processor design has shifted to parallelism for delivering high performance within constrained power budget. The growth in clock rate, processor clock rate, halted around 2005. Now, processors don't get faster by running at higher frequencies. They get more capable by having multiple cores and wider vectors on the same chip. So the number of transistors per chip keeps increasing exponentially. The Moore's law is alive and going, but there's a shift to parallelism. Here, there used to be a time that if you had application, you just would get the next Intel processor and would go faster. But that game stopped. There's no free lunch anymore. Now, application has to be optimized for parallelism for cache locality. Here are some charts from the financial modeling. 4 popular algorithms there. The first glance, you see they are all the same. They have 3 curves. The bottom one is the sequential scalar performance. That is, if you have kept it sequential and run it on the newer version of Intel processor, the performance is that the bottom thing. It's essentially improving, but not whole a lot. The major improvement comes from parallelism. The middle one is by parallelizing your application. The top one is by parallelizing and vectorizing the application. Like with parallelization, you get 32x speed up. Vectorization add another 8x. And today I'll be focusing more about the vectorization part. But if we look at browser architecture, these are the main components, the cycle breakdown. You see that the rendering part, this was done on a popular browser, mobile browser. We did this a while back. You see only about 1/3 of cycle is spent on rendering. And that is the part which is highly parallel. That scales. But the remaining, that is the 2/3 part of that, doesn't really scale. Amdahl's law tells us this won't scale unless you look at the whole thing, unless you make the whole thing parallel, make the whole thing scalable. The main problem here is that architecture of browser was essentially settled in mid-90s when the mainstream computer was single processor desktop. But now even your phones are multi-core. We need a fresh look at browser design for modern hardware. Kudos to Mozilla for the ambitious servo project, which is exactly tackling the same problem. But good progress has started happening. One of the things that we did back in the process of creating the just-in-time compiler of Firefox back in 2007, 2008 was this background just-in-time compilation. That is, instead of the main thread compiling, waiting for compilation to happen, it would put it on a queue, and it would happen on a separate core, and you would get the speed up. Although JavaScript is single-threaded, you would benefit from multi-core. And now, that model is mainstream. All browsers have that. On the chart, you basically see Firefox running one of these large games. When you have 1 million lines of C++ code, it becomes a couple million lines of JavaScript. It's a lot of compilation, but multi-core is there to help you. Very glad that it happens. Now, SIMD is another part. SIMD stands for single instruction, multiple data. That is, instead of operating on scalars, instead of doing 4 addition, you can do 1 addition, but on vectors. This was a concept from supercomputers, but now is on your phones. Now, up until now, SIMD was not available to JavaScript programmers. It's a significant part of silicon, but it's not usable. So we approached our friends at Mozilla. Who better than Brandon Ike, the creator of JavaScript? Don't know if Brandon is in the audience or not, but said, let's solve the problem. We prototyped something, and he invited John McCutcheon, a great collaborator from Google, who was trying to solve the same problem on the language Dart. And we looked at his API. We thought it was pretty good. It needed some adjustment. We did that. Now, we implemented that in 2 browsers over the course of less than 1 year, both Firefox as well as Chromium. And the Firefox part has actually landed in Firefox Nightly. So I'm going to show you some demos so you basically see the difference. Here is Chromium browser. I'm going to run Mandelbrot. This is a classic benchmark used to show SIMD, and now we are running it in the browser. I first ran it without SIMD, and you see frame per second starts from 18 frames per second and keeps going down. That is the nature of Mandelbrot. The computation, the amount of computation depends on the color. Eventually, it goes to 9 without SIMD. Now, if you add SIMD, so suddenly you come. Do you want this? That is today's web. This is what it can be. And now if you look at, leverage the wonderful tools in Chrome. I'm running this on Chrome here. We can profile it real time while it is running. And stop that. And you will basically see this is JavaScript code. We have just introduced a SIMD object. Now, I showed you this in Chromium, and I will now show you in Firefox Nightly. This has landed, and the links to all these demos are in the presentation. You can actually experience that yourself. Now, going to the web page, get here, and just run that. You see the back and forth. Now, we can actually, there is web worker, which is parallelism, higher-level parallelism, and these 2 things are orthogonal and can be compound. With SIMD, we are getting to 30, 34, so this is instruction level. If you add web workers, you're going to get even higher and higher. So this is the benefit of parallelism, hardware parallelism, and just bringing it to the web platform. So just a second. So this, the proposal was presented to the TC39 committee in the end of July. It was unanimously approved to advance to the next stage. Now, Microsoft has joined participation as well as ARM. Microsoft has actually put it on our IE roadmap. We are very, very excited about that, to see that all in all browsers. You saw all these demos. Across the benchmarks that we have, with a vector of length 4, theoretical speed limit is 4, and you're getting actually very, very good numbers. So these are essential for high-performance libraries. Now, an adjacent technology is mscripting project that Mozilla has. It compiles native code using LLVM to JavaScript. Now, we are working with them to complete the SIMD path. So if your original application, C++ application, is using the SIMD intrinsics, automatically it gets compiled to SIMD in JavaScript. It runs in the browser. And in a small benchmark here, you see we are getting almost as good as native, even with SIMD. Now I'm going to talk about bringing perceptual computing. Now, the user interface is rapidly evolving from mouse and keyboard to touch to more intuitive interaction with the computer, so that the device can sense basically your action. It can hear you, it can see you, it can recognize your gesture, it can feel you. You basically, now a major development there is the arrival of 3D cameras. A lot of computer vision algorithms are computationally expensive. 3D cameras, in addition to making it possible to do higher resolution imaging, because per pixel, in addition to color, they provide depth information, it enables you to filter out far objects, focus on the close one, and do really these complex algorithms, but even on mobile devices, on phones, and so on. So now I'm going to show you some demos here. So we have extended WebRTC, the real-time communication API of the browser, with depth stream. So it works actually in the browser without plugging, all open source technology. So I first show you one of the cool WebRTC demos. This is a Magic Xylophone, probably. You have seen that from SoundStep. So here is it asks me, and I say, yes. Now, I can play this xylophone by this. But if I come close also, you see that it plays xylophone. And that's not the way you play xylophone. So what's the reason? The reason is what this program is doing is comparing consecutive frames, pixel by pixel. That is practical. And then it finds where the motion is done. So it uses motion detection as an approximation of edge detection, which is more computationally expensive. Now, with 3D camera, we can do much better than this. Now, I'm going to put this camera, I installed that on my laptop, but as you may know, Intel has developed RealSense, which is embedded 3D cameras, and they are actually in product right now. Dell has a product, and we think it's going to be mainstream on tablets and PCs pretty soon. So now I'm going to show you one WebRTC demo using, just a second. So I'm going to, this demo was done by my colleague Ninjin Hu, who is also actually an author of this depth stream extension for W3C. And now you see I'm here, but the goal here is to cut this fruit. Now it will recognize my finger, and you see by just moving my, so I'm not supposed to touch the mom, but I do that anyway. So just image recognition, real time in the browser today. Now I am going to do that xylophone. All right, so now you see me here. See in the bottom, it just says hand. It recognizes my hand, and actually even multiple hands. And I come here, nothing happens. So this is thanks to 3D cameras. We think this is a big deal. This, coming here, let me show you a WebGL demo. So here, it's rendering me real time. So this is me, and I'm just talking to you real time using WebGL. I can enable a background. So you see the background. I can enable RGB. Now you see there are two cameras, essentially, one, and I'm here. And if I go back and filter the background, you see that happens. So this is going to bring perceptual computing to the web. This is I believe this is going to fundamentally change online shopping. When you go shopping, it can see you and then suggest things to you, and you can put clothes on, all in the web, without having to have your models before. So this is going to make it possible to scan on an object and then share it. People manipulate it, rotate it. So in addition, instead of images that are out there on the web now, you will have these 3D objects where people can interact with, navigate through that, and so on. This is going to make augmented reality a reality on the web platform. So now I have to just... To summarize, web is the most viable cross-platform technology today and is the ubiquitous application platform of the future. The web is going to be a lot more visual, more perceptual, running with the full power of the hardware platform. Thanks so much.